Guy ILS Montessori and School. Grade 9, Physics for Federal Board Islamabad, 2025 onwards syllabus. Summary of Chapter 2. Foundation of Measurement in Physics from Cantab Publishers Book. This also covers portion of Chapter 1, Physical Quantities and Measurement, of NBF Book Syllabus 2025 onwards. Summary of Chapter 2, Measurement and Physical Quantities. Introduction to Physical Quantities. Measurement is fundamental in physics, allowing us to quantify everything from atoms to galaxies. All measurable properties of matter and energy are called physical quantities, forming the foundation of physics. Physical quantities. Physical quantities consist of magnitude, numerical value, and unit, standard of measurement. For example, in 500 nanometers, 500 is the magnitude, and nanometers is the unit. These quantities allow scientists to express laws of physics and describe the world precisely. Examples include mass, length, time, force, speed, and velocity. Non-physical quantities. Some aspects of our world, like smell, happiness, and emotions, cannot be measured and are classified as non-physical quantities. Base and derived quantities. Physical quantities are classified into two categories. 1. Base quantities, fundamental quantities that are measured directly, such as length, mass, time, temperature, electric current, luminous intensity, and the amount of substance. These form the basis of all physical measurements. 2. Derived quantities, quantities formed by combining base quantities through calculations, like speed, length, time, area, volume, and force. These help in understanding various physical phenomena. The relationship between base and derived quantities is essential for comprehending the physical world and its laws. Introduction to SI units. Before making measurements, a standard unit must be chosen. The International System of Units, SI, was agreed upon by scientists in 1960 and refined in 1970. It is a coherent and complete system of measurement based on the metric system, where units are divided or multiplied by 10 to create smaller or larger units. Base units and derived units. SI consists of 7 base units that are used to define all physical quantities. 7 base quantities and their units. Mass, kilogram, kilogram. Length, meter, m. Time, second, s. Electric current, ampere, A. Thermodynamic temperature, Kelvin, K. Amount of substance, mole, mol. Luminous intensity, candela, CD. These base units are measured directly and serve as the foundation for defining all other physical quantities. Examples of derived quantities and their formulas. Area, A, length times breadth. Volume, V, length times breadth times height. Velocity, V, displacement divided by time taken. Acceleration, A, change in velocity divided by time taken. Momentum, P, mass times velocity. Density, Rho, mass divided by volume. Force, F, mass times acceleration. Pressure, P, force divided by area. Frequency, F, 1 divided by time period. Work, W, force times displacement. Power, P, work divided by time taken. Derived quantities are calculated from base quantities using mathematical operations like multiplication or division. These quantities are crucial for understanding physical phenomena. Scientific notation. Large or small values are expressed using scientific notation, which simplifies calculations and representations. It follows two rules. 1. The number is written as a times 10 to the power of n, where a is a digit between 1 and 10, integer or decimal. 2. N is positive for numbers greater than 1 and negative for numbers less than 1. For example, 300 is written as 3 times 10 to the power of 2, 0.005 is written as 5 times 10 cubed. SI prefixes and estimation. The vast range of physical quantities, from the radius of Earth, 6,400 kilometers, to the size of an atom, 0.1 nanometers, requires a method to manage values efficiently. SI prefixes help in expressing very large or very small values easily. Prefixes and their multipliers. Kilo, K, 10 to the power of 3, 1000. Milli, M, 10 cubed, 0.001. Micro, mu, 10 to the power of 6, 0.000001. Nano, N, 10 to the power of 9, 0.00000001. For example, 2000 meters equals 2.0 times 10 to the power of 3 meters equals 2.0 kilometers, km. Order of magnitude. The order of magnitude helps compare values by expressing them in powers of 10. 800 is 8 times 10 to the power of 2, and 450 is 4.5 times 10 to the power of 2, so both have the same order of magnitude, 10 squared. Estimating a physical quantity. Estimation helps in making quick and reasonable approximations. Some methods include using orders of magnitude, estimating based on known sizes, referring to known quantities, comparing with familiar measurements, applying logical reasoning, making educated guesses based on experience. Conventions for writing SI units. Unit symbols are written in lowercase, except when named after a person, e.g., meter, m, but ampere, a. Prefixes are written without spaces, e.g., km for kilometer. Multiplication of units is shown with a space or dot, e.g., nm or nm. Division of units is written with a slash or negative exponent, e.g., meter per second or ms. Numbers and units have a space between them, e.g., 25 kilograms, not 25 kilograms. Large numbers are written with spaces instead of commas, e.g., 15,739. Only one prefix is used at a time, e.g., 10 nanoseconds, not 10 meters µs. These conventions ensure clarity and consistency in scientific communication. Measuring small time intervals, the time period of a simple pendulum. To discuss the concept of average in measuring small time intervals, we take the example of measuring the time period of a simple pendulum. When you pull the bob to one side and release it, it swings back and forth. The time taken to complete one swing is called the time period. To measure the time period, you can use a stopwatch, but keep in mind that your reaction time when starting and stopping the stopwatch may affect accuracy. To minimize this effect, measure longer time intervals compared to your reaction time. For example, if the pendulum takes 2 seconds for one swing, count the time for multiple swings, like 30 swings taking 54.5 seconds. Calculate the time period by dividing the total time by the number of swings. Time period equals total time divided by number of swings. Example, 54.5 s divided by 30 equals 1.82 s. To reduce random errors, repeat this process at least 3 times and calculate an average for more accurate results. Understanding measurement concepts. After learning about errors in measurements, it is important to delve into the concept of the least count of a measuring instrument. Understanding the least count is essential for achieving accurate measurements. It gives insight into the precision of our measurements. Also, minimizing systematic errors and reducing random errors contribute to improving measurement precision and accuracy. Therefore, grasping these concepts is critical for obtaining reliable measurements in experiments. Least count of data collection instruments. Analog, from its scale. Understanding the precision of our measuring instruments is key in scientific studies. The least count, LC, of an instrument is the smallest difference in a reading that the instrument can measure, or the smallest measurement that can be taken accurately. It can be regarded as the resolution of the instrument. The least count helps to minimize errors in measurement. Examples of least count in common instruments. Ruler. If a ruler has markings at each millimeter, its least count is 1 millimeter. Stopwatch. The least count of a stopwatch can vary. For digital stopwatch, 0.01 seconds. For analog stopwatch, 0.1 seconds. To measure the least count of a stopwatch. For an analog stopwatch, observe the smallest division between consecutive markings on the dial. For a digital stopwatch, note the last decimal place displayed on the stopwatch. If the display shows up to 2 decimal places, the least count is 0.01 seconds. Limitations in using measuring instruments. Selecting the right measuring tool is crucial for accuracy. For large objects, e.g., bookshelves, a meter rod that measures to the nearest millimeter works well. For precise measurements, e.g., diameter of a wire, a screw gauge with a 0.01 mm minimum value is required. Using the incorrect tool can result in significant measurement errors. The least count of a measuring instrument is crucial for understanding its precision and accuracy. A smaller least count indicates higher precision and the ability to make finer distinctions, contributing to more accurate scientific experiments and observations. Precision and accuracy. Precision. The ability of an instrument to provide highly exact and detailed measurements. High-precision instruments offer measurements with more significant digits. The smallest measurement possible is determined by its least count. Example, a micrometer screw gauge, 0.01 mm precision, is more precise than vernier calipers, 0.1 mm precision. Accuracy. How close measurements are to the true or accepted value. Accuracy is affected by random and systematic errors. Reducing errors improves accuracy. Types of measurement accuracy and precision. 1. Inaccurate and imprecise. Measurements are not near the true value and not close to each other. 2. Precise but inaccurate. Measurements are consistent but not close to the true value. 3. Accurate but imprecise. Measurements are close to the true value but not consistent. 4. Accurate and precise. Measurements are both close to the true value and consistent. Techniques of measuring length. Mastering the art of measurement is a foundational skill in science. This section explores the use of common laboratory instruments to measure length, volume, and time accurately. Length measuring instruments. A. Measuring tape. Used for long distances with limited accuracy. Common in sports events, e.g., long jump, shot put, javelin. Can measure several meters but has a least count of 1 centimeter or 1 millimeter. Useful for curved or non-straight distances. B. Meter rule. Commonly used in laboratories. Length. 1 meter equals 100 centimeters equals 1000 millimeters. Least count, 1 millimeter. Common errors in length measurement. 1. Systematic and random error. To avoid zero error, measure an object's length using 2 readable points instead of starting from 0. Some instruments may have built-in zero errors. 2. Parallax error. It is caused by an incorrect viewing angle. To reduce parallax error, keep your eye directly over the measurement point. Ensure your line of sight is perpendicular to the scale. 3. Random error. A meter rule may have limitations in its last digit reading. To minimize this, use a more precise instrument such as vernier calipers. Vernier calipers. A meter rule measures up to 1 mm, but vernier calipers offer more precision. The main scale is in cm and mm, while the vernier scale has 10 divisions of 0.9 mm each. The least count, LC, is 0.1 mm, calculated as least count equals smallest division on main scale divided by number of divisions on vernier scale, equals 1 mm divided by 10 equals 0.1 mm. Procedure to take reading on vernier caliper. 1. Read the main scale mark just before the 0 of the vernier scale. 2. Find the vernier scale mark that aligns with the main scale. Multiply this mark by 0.01 cm. 0.3. Final reading equals main scale reading plus vernier scale reading. Systematic error on vernier caliper. Zero error occurs if the zero marks of the scales don't align when jaws are closed. Positive error happens when the vernier 0 is right of the main scale 0, negative if left. Correct the reading by subtracting the zero error. Random error on vernier caliper. Random errors arise from alignment inconsistencies. Minimize them by averaging multiple readings and maintaining stable conditions. Micrometer screw gauge. The screw gauge measures smaller lengths with higher precision than vernier calipers. The spindle moves 1 mm per full rotation, with 100 divisions on the circular scale. Least count equals 1 mm divided by 100 equals 0.01 mm. Procedure to take reading micrometer screw gauge. 1. Secure the object gently between the anvil and spindle. 2. Read the main scale in mm, adding 0.5 mm if needed. 3. Multiply the aligned circular scale mark by 0.01 mm. 4. Final reading equals main scale reading plus circular scale reading. Systematic error on micrometer screw gauge. Zero error arises if the scale zeros don't align when fully closed. Positive error occurs if the circular zero is below the index line, negative if above. Correct the reading by subtracting the zero error. Random error micrometer screw gauge. Random errors occur due to pressure differences. Use the ratchet to maintain constant pressure. Measurement of volume of liquid and solid. Volume is the space an object occupies, measured in m cubed, cm cubed, or dm cubed. Liquid volume measurement. Use a measuring cylinder. Read the liquid level at the bottom of the meniscus. Regular shaped solid volume measurement. Use formulas like volume of a cube equals length cubed, volume of a sphere equals 4/3 pi r cubed. Irregular shaped solid volume measurement. Submerge the object in water and measure the water rise. For large objects, use a displacement can. Precautions for measuring volume. Keep your eye level with the meniscus to avoid parallax errors. Measurement of time interval. Time intervals help track processes and events, using a stopwatch. 1. Learn the controls. 2. Start the timer when the event begins. 3. Stop the timer when the event ends. 4. Note the elapsed time. 5. Reset and repeat for accuracy. Data interpretation and rounding off calculations. Rounding off numbers. 1. If the digit dropped is less than 5, keep the last digit, and if it is greater than 5, then add 1 to the last digit. 2. If the digit is exactly 5, round to the nearest even number. Significant figures. Non-zero digits are always significant. Zeros between digits are significant. Zeros to the left are not significant. Right-hand zeros are significant in decimals. Significant figures in calculations. For addition, subtraction, match the least decimal places. For multiplication, division, match the least significant figures. That is the end of chapter 2.